It's not uncommon for people to look through a telescope for the first time and get disappointed. Not because observing through a telescope isn't cool, it's quite the opposite. It's because prior to that, they saw images captured by telescopes like Hubble, and then they expected that looking through the eyepiece of a regular telescope, they would see something similar to that. And that, of course, is not the case. Partially because our eyes can't accumulate light over a long period of time like cameras can. But when you know what you're looking for and understand what to expect, even observing a blurry spot, you get a thrill from realizing that it's the core of a distant galaxy. But there are objects that can impress even unprepared people when observed through a telescope. And one of them, of course, is Saturn. When I show Saturn to people through a telescope, I almost always hear them gasp, "Wow," right away. Even at not very high magnification, when you see that it's not just a point of light and not even a bright disk where you can barely make out any details, but you can clearly see the planet's shape with its rings, it leaves an impression. It is the year 1610. Galileo Galilei first in history sees Saturn's rings through a telescope and makes sketches like these. 407 years later, a spacecraft created by humans flies between the planet and its rings. On the one hand, during this time period, especially in recent decades, we've learned a lot about Saturn's rings. On the other hand, much still remains a mystery. And perhaps the main mystery is where these rings came from. Yes, we don't really know that. Of course, there are theories, but they all have their problems. And a great indicator of this is estimates of the age of the rings. The maximum estimate is 450 times greater than the minimum one. Quite a margin of error. Today we'll talk about Saturn's rings, their unusual properties, the paradox of their age, and the theories of their formation. My name is Andrei, and this is Cosmos Elementary. What's so remarkable about Saturn's rings anyway? On the one hand, when we say a planet with rings, we immediately think of Saturn. And until relatively recently, it was indeed the only known object with rings. The second was the discovery of the ring system of Uranus. However, the exact timing of this discovery is not quite clear. Some sources claim that they were discovered in 1977 by James Elliott. Here's the original paper about the discovery. But as early as 1787, William Herschel wrote that he observed rings around Uranus. However, many astronomers doubt that he could have actually seen them. Uranus's rings are very faint, and after Herschel, almost 200 years passed without anyone seeing them. And even Elliott didn't just see them through a telescope, as in the case of Saturn, but discovered their presence during an occultation, when the planet passes in front of a background star and briefly blocks its light. If a planet has rings, then at a certain angle, we'll see multiple drops in the star's brightness, as the planet blocks it. And the less significant brightness drops tell us about the presence of rings. Here's an example of the light curve of a distant star during Uranus's occultation. The blue line represents the change in brightness of the star over time. If there were no rings, we would only see this strong drop on the graph, from Uranus itself. But we also see 3 smaller drops, before and after the planet's occultation. This indicates the presence of separate rings. In any case, we now know that in the solar system, rings exist around all 4 giant planets. Jupiter's rings are exaggerated in this image. And that's, for instance, an infrared image of Neptune's rings obtained by James Webb Telescope. But none of the ring systems compare to Saturn's in terms of brightness, extent, variety of structure, and so on. Rings are known to exist around a dwarf planet, namely Haumea, and even around asteroids, such as the large centaur Chariklo. That's within the solar system. Beyond our solar system, among exoplanets, considering that even detecting their presence is not so straightforward, we don't really know much about planetary rings. However, there is one very interesting candidate. Often, to name types of exoplanets, we use analogs to planets in our solar system, like hot Jupiters, mini Neptunes, super Earths. So a planet J1407b has been dubbed Super Saturn, This is because data suggests that this planet doesn't just have rings. Those rings are enormous. The system consists of more than 30 rings, each of which is tens of millions of miles in diameter. This ring system could be 200 times larger than Saturn's ring system. And it's quite possible that many other exoplanets have rings, we just haven't seen them yet. Furthermore, if we're talking about not only rings around planets, but also about fairly flat disks of material, they're actually quite common in the universe. Initially, amorphous structures like fragments of vast gas and dust clouds undergo gravitational collapse, forming new stars, around which protoplanetary disks appear. And in turn, planets are formed within those disks. A rotating collection of matter tends to take on the disk shape, thanks to the conservation of angular momentum. And this is why planets in our solar system are primarily located in one plane, and also move along orbits and rotate predominantly in the same direction, because they were formed in one flat rotating disk. One could see quite a few similarities between a young star system surrounded by a protoplanetary disk and young planets within that disk, and a gas giant like Saturn, with its ring system and numerous moons, including those within the rings. So, what's the problem then? It seems that planetary rings are quite common, essentially half of planets in the solar system have them. Surely there are many of them in the galaxy, disks are quite common. Why can't we settle on a single coherent theory of their formation? And when I compare the star with a protoplanetary disk and Saturn, did you see the catch? Well, yes, disks are found around young stars. That super Saturn exoplanet is also young. But Saturn, like the entire solar system, is approximately 4.6 billion years old, which is not what I would call particularly young. Yes, other giant planets have rings, but they are far from Saturn's rings, and their appearance is easier to explain. But bright and massive rings like Saturn's raise a lot of questions. Take for example the problem of age that I mentioned. Let's now delve into the details of those issues. When observed through an amateur telescope, Saturn's rings may appear as a single object, but they are not called a ring for nothing. They're called rings because they consist of multiple separate rings. Still, even from Earth, through a telescope or in images, you can already discern the so-called Cassini division, which shows us that they're not as solid as they might seem. Observations from Earth for a long time were all we had. But then spacecraft like Pioneer 11 flew past the planet. Here is a photo from Pioneer. The Voyagers, their flyby images led to new discoveries. However, in those cases, the time spent observing the planet and its rings from the close proximity was short. And the bulk of information about the rings was obtained thanks to the Cassini spacecraft, which was the first to orbit Saturn and spent 13 years studying the system. Cassini provided valuable data on the composition, structure, temperature, dynamics, and mass of the rings, and after the mission our knowledge about them was on a completely different level. Saturn's rings are a complex and diverse system of rings. Partially for this reason, it's not easy to talk about their formation because it's not a single object, but rather, well, a system. I won't go into too much detail about their entire system right now and won't describe all the variety of effects, structures and phenomena present in the rings. It would take a whole separate video, perhaps even not one. Today let's focus on their formation, but we'll briefly touch on their structure and properties. Firstly, the ring system is enormous. Its diameter is about 280,000 kilometers or about 175,000 miles. If you were to place Saturn's rings around the Earth, they would almost reach the Moon. More precisely, would be about 3/4 of the distance. At the same time, they are incredibly thin. On Earth, we experience changes in seasons because the planet's axis of rotation is tilted relative to its orbit around the Sun. And Saturn is also tilted just a bit more than Earth, at about 27 degrees compared to Earth's 23. And when we observe Saturn from Earth, the planet's tilt and consequently its rings tilt, which lie along the equator, constantly change. And check out this cool animation made from shots taken over the years. When the rings are turned edge on to us, they practically disappear. With a diameter of hundreds of thousands of kilometers, their thickness barely reaches a few dozen meters. Here's a shot of the rings almost edge on. And here's another shot where the rings are again almost edge on and are barely visible. But dozens of meters, it's the average. Naturally, the rings consist of billions, if not trillions of individual objects, ranging in size from grains of sand, and in some rings they may even resemble smoke or vapor particles. But there can be fairly large ones, tens or even hundreds of meters in diameter. And the rings are composed mostly of ice, 95 to 99%. And only a small part of what we would call dust or dirt. In general, various silicates and metals. And such proportions are strange, and we will talk about this further. The measurements from the Cassini spacecraft showed that the mass of the rings comprises approximately 40% of the mass of Saturn's moon Mimas, a small icy moon with a diameter of about 400 kilometers. The ring system is divided in separate rings, each assigned a letter as its name. By the way, don't be surprised that the rings often look different in pictures. This depends, for example, on the perspective. When the sun shines on the rings from above, the images from the lit or shadowed side will look different. In such a perspective, when the sun is behind the observer and illuminates the planet, it's easy not to see all the rings. Here we can see the main rings A, B, and C, and the innermost ring D, and the narrow ring F. In such images from Cassini, we can see that even the main rings themselves have their own complex structure. But from this perspective, when the sun is behind the planet and illuminates it and the rings, the fainter and more diffuse rings G and the ring E become visible. Now I'll show you a cool animation where the rings are clearly highlighted. The rings D, C, B, A, F, G, and E. Actually, even further out, the so-called Phoebe ring, another ring of Saturn, was discovered. And it is located much farther from the others, in the orbit of Saturn's distant moon Phoebe. Here is roughly its size, although in reality it's practically invisible. It was discovered using infrared observations from the Spitzer Space Telescope, and we won't consider it today. Of course, the entire structure of the rings is much more complex, and there are still many regions with individual names. There is a lot of interesting things happening with the interaction between moons and rings, but we'll save that for another time. It's worth noting that the origin of at least one ring is fairly well understood, but it differs from others. This is the E ring, which consists not of chunks of ice, but rather of microscopic particles of ice, silicates and some other substances. The Cassini spacecraft discovered that the source of the material is Saturn's moon Enceladus, which resides within this ring. Water plumes from beneath Enceladus' surface supply this ring with material. But when it comes to the main rings, things get more complicated. The major barrier in constructing a theory of Saturn's ring formation is determining their age. We determine the age of cosmic objects in various ways. The age of stars can be approximately determined because, well, firstly, we can measure several parameters of stars, such as their mass, luminosity, temperature, and composition. Secondly, we can observe a large number of stars that are very similar to each other in these properties, but at different stages of evolution, from their birth to their death. Based on that, we can build models of stellar evolution and compare, let's say, a new star to those models and determine roughly what stage it is in, hence its age. In the solar system, we study the oldest available meteoritic material in laboratories and determine its age using radioisotopic analysis. I talked about this in more detail in my video on presolar grains. And by correlating the results of these analyses with the other data, we estimate that the solar system, including the Sun, planets, and other bodies, is approximately 4.6 billion years old. Actually, the planets formed slightly later than the Sun, but the difference is not that big. It's millions of years rather than billions. We can also determine the age of some bodies, for example, by counting the number of craters on their surface. The more craters, the older the body, if the surface is not being renewed somehow. But it is obvious that none of these methods are suitable for determining the age of the rings. More precisely, we can at least establish an upper limit on their age and say that the earliest they could have formed is along with the planet Saturn itself. Let's say they're remnants of a circumplanetary disk from the time of the planet's formation, so they would be approximately 4.5 billion years old. On the web, you could find drastically different estimates, from 10 to hundreds of millions of years and even more. That's quite a range, from 10 million to 4.6 billion years. The catch is that there are arguments both for young and old rings. And some of the current theories of formation are based on one estimate, while others on another. If the rings are indeed 100 million years old or less, it means that if dinosaurs had telescopes and could observe Saturn, it would have appeared to them as a rather unremarkable planet. But where did the idea that the rings could have formed so recently come from in the first place? The discussion became particularly active after the Cassini mission data became available, but the idea had been raised earlier, as far back as the late 1980s. Scientists wrote that over billions of years, the rings could simply disappear. When a large protoplanet presumably collided with young Earth, which eventually led to the formation of the Moon, Earth was also surrounded by a disk of material for some time, but we don't see it now. There are hypotheses that Mars may have had rings in the past, but if they existed, they either fell onto Mars, formed the Moon, or just dissipated. Particles of rings of Saturn also experience constant collisions and feel drag. The International Space Station, while orbiting at an altitude of 400 kilometers or about 250 miles above Earth, gradually loses altitude due to atmospheric drag. Although it is nearly vacuum there is still some material at that height. The extremely rarefied atmosphere of Earth extends for thousands of kilometers, and this is enough to gradually slow down the ISS and other satellites. And that is why the orbit of the ISS needs periodic adjustments and boosts by firing its engines. And particles in the rings, well, don't have engines, so all of this could lead to the rings' dissipation. Materials from the rings fall onto the planet even now. And once again, there are theories that at such rates they could disappear completely relatively soon. Considering how massive they are now, it's amazing that they've managed to survive. Of course, we don't know their original mass. It's possible that they were much larger before, and what impresses us now is just a pale shadow of their former selves. But again, we don't know their initial mass. The second argument is the darkening of the rings. Thousands of tons of cosmic dust fall onto Earth annually. Earth has a dense atmosphere, and most of this material burns up in the atmosphere. However, surfaces of bodies without atmospheres gradually accumulate cosmic dust, and if there is no mechanism to renew the surface, like cryovolcanism, geysers, or tectonic activity bringing fresh ice to the surface, such a surface should darken over time. And once again, in the late 80s, scientists believed that Saturn's rings should darken over time, but now we have data from Cassini, and here's what they tell us. Firstly, Cassini measured the mass of the rings. Furthermore, we have data on the composition, which indicates that contaminants may be only 5% or even just 1%, with the rest being ice. And thirdly, Cassini measured the flux of this dust, how much of it falls over a certain period of time. Knowing all this, scientists calculated that at this rate of dust deposition, the rings should have reached current contamination level within 100 million years. Hence, such an estimate of their age. Well, does that mean the problem is solved? Not quite. For this estimate to work, we need to make three assumptions. First, that the mass of the rings is constant. Second is that dust flux remains constant as well. And also that the rings cannot rid themselves of the contamination. That's possible, but another problem arises. If the rings are so young, how did they form? And if they are ancient, why do they look so young? Let's go through several hypotheses and their pros and cons. First, the rings remaining since the very beginning of the planet's formation. The emerging gas planet accumulating material was supposed to form a flat disk of material around itself, from which satellites later formed. According to this version, the rings are simply remnants of that disk. Firstly, here we don't need to make assumptions about the age of the rings. Furthermore, it's good that rings are usually in the same plane as the satellites and orbit and rotate in the same direction, meaning they have a lot in common between them. I already mentioned the problem with this hypothesis. It's unclear how such massive rings have survived to the present day. The composition of the rings is also an issue. Why are they almost entirely made of ice? Where did the silicates, rocky materials, go? They should have been there originally, but for some reason they haven't been preserved. Another major hypothesis, or rather a group of hypotheses, is that the rings are the remnants of a destroyed moon. Supporting this idea is the mass of the rings, which is indeed comparable to the mass of a small satellite like Mimas. However, now we know that it's slightly less than half its mass. This raises a question of how this satellite could have been destroyed. Firstly, there is this scenario. A satellite that was initially farther away from the planet ended up inside the Roche limit. This is the distance from the planet within which tidal forces become so strong that they tear the satellite apart. Can a satellite's orbit decrease like this? In the young planet's disk of material, a satellite can approach the planet due to interactions with the material in the disk. Or similar to how hot Jupiter's, exoplanets resembling Jupiter, which are likely originally formed far from the star but then migrated to a region close to the star. Could such a thing happen? Certainly, but there is a problem with this theory. Just tidal disruption alone probably couldn't create such rings, as it is not capable of breaking the satellite into centimeter and millimeter sized particles. Therefore, this scenario needs to be even further complicated. When the moon reaches a Roche limit, another body, such as a comet, needs to collide with it. This could have occurred during the period of the so-called late heavy bombardment, when large collisions were much more frequent in the early solar system than they are now. This scenario presents a plausible mechanism for formation. Moreover, for other planets, rings may have formed precisely as a result of the disruption of satellites, and it also explains the large mass of the rings. But then the age of the rings should be around 3.8 or 3.9 billion years, which doesn't agree with their apparent youth. And again, it doesn't explain why the rings are almost entirely composed of ice. Icy moons typically don't consist entirely of ice. They usually have a silicate or metallic core or a silicate mantle. And where did the material from the core go? There is another hypothesis involving moon destruction that partially addresses this issue. Here, a larger satellite is involved, not the size of Mimas, but the size of Titan. An icy satellite with a core of silicates also falls within the Roche limit. Tidal forces don't entirely destroy it, but strip away the icy mantle from the satellite, while the rocky core withstands and falls onto the planet, and the material from the mantle becomes the rings. This answers the question of why the rings consist almost entirely of ice. There is a similar idea where instead of a satellite, tidal disruption of a large comet with a nucleus radius of over 300 kilometers is considered. Passing by the comet could come under Saturn's gravitational influence, ultimately ending up beyond the Roche limit and got disrupted by tidal forces. Something similar to what happened to comet Shoemaker-Levy 9, which was destroyed when it came too close to Jupiter. This event was even observed by astronomers. However, for the formation of rings with Saturn, it should have occurred on a much larger scale, but here again there is an issue with age. Such a close flyby of a large comet near the planet could have occurred in the early chaotic solar system. However, if the rings are young, then the chance of such an event happening 100 million years ago is very, very low. If we go back to considering satellites, even in not so distant past, due to some instability in Saturn's system, satellites could have collided, and the resulting fragments formed rings. But if the rings are indeed ancient, why do they appear so young? Why is there so little dirt in them? Well, one possibility is that the rings might clean themselves, and there are even some indications of that. Since the time of Voyager missions, we know that ring material falls onto the planet. This is sometimes referred to as ring rain. Measurements from Cassini show that for some reason, this ring rain removes a much larger proportion of silicates from the rings. Despite over 95% of rings being composed of ice, only 24% of this rain is ice. In other words, the material falling onto the planet is mostly dirt. Traces of this ring material have been detected in the planet's atmosphere. The tricky part is that no one knows why this happens yet. In general, there are still too many unknowns. We don't know how consistent the dust precipitation is, we don't know the initial mass of the rings, perhaps material in the rings is still being replenished, and lots of other uncertainties. Among scientists, there are proponents of both young and old ring theories. However, it's evident that making definitive conclusions at this point is not really possible. And of course, there are many nuances like the influence of magnetic fields, which I haven't touched upon. Perhaps future missions to Saturn with more advanced equipment will clarify the situation. And also, if the hypothesis that the rings will disappear in just 300 million years is true, and if they are appeared recently, it means that we're lucky to live during a short period, well, by the universe's standards, where we can observe Saturn's impressive and beautiful rings. Thanks for watching. Links to all of the sources are as always down below in the description, and if you enjoyed the video, leave a like, comment, subscribe for more videos in future. Bye!